Hello friends, I welcome you in lecture number 15 on relations. In this lecture we are going to discuss operations on relations. So before going for operations on relation, we just recall the definition of a relation. We know that if we have two sets, say A and B, then relation from A to B is a subset of the Cartesian product A cross B. Relation R from set A to set B is a subset of the Cartesian product A cross B. Therefore, relation itself is a set. So, relations are nothing but special types of sets, and we have discussed operations, different operations on sets. For example, we know how to take union of two sets, intersection of a set, complement of a set, difference of sets, symmetric difference of sets, etc. So because relations are sets, we can apply all the operations on sets which we have discussed in the unit of set theory. So here we are going to combine relations using different operations, and we are going to discuss problems which will have operations on relations. So as I discussed, a relation has been defined as a set of ordered pairs because it is a subset of Cartesian product. Members of the relation are nothing but ordered pair xy, where x comes from the first set and y comes from the second set. So relation is a set of ordered pairs. Therefore, it is possible to apply the usual operations of sets to relations as well. The resulting sets will also be ordered pairs and will define some relation. For example, if I have two relations, say R1 and R2, then I know that R1 and R2 are subsets, therefore they are sets, therefore I can talk about union of these two relations. So this new relation, this new set will also define a relation. Similarly, we can talk about intersection of two relations R1 and R2. We can talk about complement of the relation. We can talk about difference of relations. We can talk about symmetric difference of relations. So all the operations which we have discussed in set theory, all those operations we are going to discuss for relations here, because relations are itself set of ordered pairs. So first I have taken these two operations on relation, union and intersection of relations. If R and S denote two relations, then R intersection S defines a relation such that R intersection S contains those ordered pairs xy such that ordered pair xy is present in R as well as ordered pair xy is present in S. R intersection S is nothing but collection of those ordered pairs xy which satisfy these two conditions. Ordered pair xy belongs to R and ordered pair xy belongs to S. Similarly, union of R and S is a relation such that ordered pair xy belongs to R union S if and only if ordered pair xy belongs to R or ordered pair xy belongs to S. So here we are simply using the definition of union and intersection operations of sets for relations also, because relations are also some special types of sets. So here I have taken this example to explain the union and intersection operations on relation. Suppose X is a set containing 4 positive integers 1, 2, 3, 4. Relation R is defined on this set X as the collection of those ordered pairs xy such that xy belongs to this set capital X, and x minus y is an integral non-zero multiple of 2. That is, difference of two integers is a multiple of 2 and that difference must be integer and it must be non-zero. S is defined as ordered pair xy where xy belongs to x and x minus y is an integral non-zero multiple of 3, and here we have to consider x and y from this set capital X. So simply here R and S are relations on this set X, therefore R and S are nothing but subsets of X cross X. They are subsets of Cartesian product of X with itself. And we have to decide union of R and S and intersection of R and S. This is part A. In part B, instead of this set capital X, they have given capital X equal to set of all positive integers 1, 2, 3 and so on. This is nothing but set of natural numbers n. So if X is replaced by set of natural numbers, then we have to answer that in that case what is intersection of R and S for R and S as defined in part A, that is R and S are same, they have replaced capital X by the set of natural numbers. So we will discuss both the parts one by one. First we concentrate on part A. Given set has 4 elements 1, 2, 3 and 4, and we are given two relations on set X, that is we have to consider subsets of X cross X satisfying those two conditions 1, 2, 3, 4, Cartesian product of 1, 2, 3, 4 with itself 1, 2, 3, 4. So this means we have to consider all those ordered pairs x, y using this Cartesian product where x and y are from these 4 natural numbers. So I am not writing the whole Cartesian product, but elements will look like this 1, 1, 1, 2, 1, 3, 1, 4, and this we have to repeat for each of the numbers, that is 2, 1, 2, 2, 2, 3, 2, 4, then 3, 1, 3, 2, 3, 3, 3, 4, 4, 1, 4, 2, 4, 3, 4, 4. So if you wish you can write that whole Cartesian product, but it is not necessary. We are interested in the definition of R and S. So among all those ordered pairs from X cross X, we have to consider those ordered pairs XY such that X minus Y is an integral non-zero multiple of 2. That is the definition of relation R. Relation R is given by ordered pair x comma y such that x y belongs to capital X and x minus y is an integral. Integral means x minus y is an integer, is an integral non-zero multiple of 2. That is difference is non-zero multiple of 2 and difference is also an integer. So we have to decide which ordered pairs belong to relation R. So we can start in this way. First I fix 1, so I have to check for 1, 1. So 1, 1 belongs to R if 1 minus 1 is an integral non-zero multiple of 2. So we know that 1 minus 1 is 0. So 0 can be written as multiple of 2, but 0 is not allowed. We are allowed only non-zero multiples of 2. So 1, 1 is not in R. Then we have to check for 1, 2. So if we take the difference of 1 and 2, it is minus 1. So minus 1 is not multiple of 2. Then we have 1, 3. I have fixed 1 here and I am changing this second component for ordered pairs. So 1, 1 is not in R, 1, 2 is not in R. Now I am checking for 1, 3. So I have to check whether 1 minus 3, that is minus 2, is an integral non-zero multiple of 2. So minus 2 can be written as minus 1 into 2, and this minus 1 is integer. Therefore 1 minus 3 is an integral non-zero multiple of 2. Therefore this ordered pair 1, 3 belongs to relation R. So in this way I have to check for each possible pair, and I will write down those pairs in relation R for which x minus y is an integral non-zero multiple of 2. Now next pair is 1, 4. So 1, 4, that is 1 minus 4, which is minus 3, and this is not multiple of 2, so we will not take 1, 4. Now we fix these two as first component and we vary second component. Then I will consider 2, 1. So difference of 2 and 1 is 1, which is not multiple of 2. Then 2, 2. Difference of 2 and 2 is 0, but 0 is not allowed. Then 2, 3. Difference of 2 and 3 is minus 1, which is not multiple of 2. Then 2, 4. So difference of 2 and 4 is minus 2, which is multiple of 2. So I will write down ordered pair 2, 4. So I have finished for second component. So in this way I have to check for each component. Now I fix this 3. So we can directly check now 3, 1. 3 minus 1, that is 2. So it is multiple of 2, so that is allowed. 3, 1 is allowed. Then 3, 2. So I have to check whether 3 minus 2 is multiple of 2 or not. 3 minus 2 is 1, which is not multiple of 2. 3, 3 is not allowed, difference is 0. 3, 4. So 3 minus 4 is minus 1, which is not multiple of 2. Now we check for last one, that is 4. So first I will consider 4, 1. So 4, 1, difference is 3. So it is not allowed. Then 4, 2. Difference of 4 and 2 is 2, that is multiple of 2. Then 4, 3. Difference is 1. So that is not multiple of 2. And 4, 4. So 4, 4 is also not allowed. Difference is 0. So these are the ordered pairs in the relation R. Similarly, I have to decide the ordered pairs in the relation S. So for S, I have to consider those ordered pairs for which x minus y is integral non-zero multiple of 3 and x minus y is an integral non-zero multiple of 3. So let's check for all the ordered pairs, and we check which ordered pairs belongs to S. So again we start with first component. So I have to check for 1, 1. 1 minus 1 is 0, not allowed. Then 1, 2. 1 minus 2 is minus 1, which is not multiple of 3. Then 1, 3. 1 minus 3 is minus 2, which is also not multiple of 3. Then 1, 4. For 1, 4, we have 1 minus 4 is minus 3, which is a non-zero multiple of 3. Therefore 1, 4 belongs to relation S. Similarly, now I check for 2. 2, 1. 2 minus 1 is 1, not allowed. 2, 2, 0, not allowed. 2, 3. 2 minus 3 is minus 1, which is not multiple of 3. Then 2, 4. Difference is minus 2, which is also not multiple of 3. So now we come to this part. 3, 1. Difference is 2, not allowed. 3, 2. Difference is 1, not allowed. 3, 3. Difference is 0, not allowed. 3, 4. Difference is minus 1. So there is no ordered pair corresponding to 3. Then 4. So 4, 1. So difference of 4 and 1 is 3. So that is allowed. So we write ordered pair 4, 1. Then 4, 2. Difference is 2, not allowed. 4 3 difference is 1 not allowed, 4 4 difference is 0 not allowed. So these are the only ordered pairs which belongs to relation S. So now I have two sets R and S, sets of ordered pairs, and I have to decide their union first and their intersection. And we know that union of two sets is the collection of all the members which are present in R as well as in S as well as in both the sets. So I am writing all the members. First I am writing members of R: 1 3, order pair 2 4, order pair 3 1, order pair 4 2, and then for order pair 1 4 members of S. This is union of R and S, and similarly I have to decide R intersection S. R intersection S means the members which are common to R and S, or the elements which belong to R as well as S. So we can see 1 3 is not present in S, 2 4 is also not present, 3 1 and 4 2 are also not present in S. Or we can check for these two elements, they do not belong to R, therefore there is no member which is common to R and S, therefore intersection is empty set. Now in second part, our set X is replaced by the set of natural numbers, that is now we have infinite set. So here capital X is an infinite set, set of all natural numbers 1 2 3 and so on, or we can simply write n. Therefore this X cross X, Cartesian product of X cross X, is also an infinite set, 1 2 3 and so on, 1 2 3 and up to infinity. And in this part R and S are defined as in part A, and we have to decide the intersection of R and S. So here we have infinite number of elements in X cross X, therefore R and S will also have infinite number of elements, because R is the set of all ordered pairs for which X minus Y is an integral non-zero multiple of 2. So there are infinite number of ordered pairs possible. Similarly, ordered pair XY for which X minus Y is non-zero multiple of 3 belong to S. So there are infinite number of elements which are present in R and S, and we have to decide among those, we have to decide those ordered pairs for which ordered pair XY is multiple of 2 as well as ordered pair XY is multiple of 3. So we can think in this way, for relation R ordered pair XY is multiple of 2. So I can write that X minus Y equal to 2 into K1, where K1 is non-zero integer. And for S, I have to collect those ordered pairs for which difference is multiple of 3. So say 3 times K2, where K2 belongs to Z and K2 is non-zero. And for R intersection S, I have to collect those ordered pairs for which this X minus Y is multiple of 2 as well as X minus Y is multiple of 3. And we know that 2 and 3 are having their least common multiple as 6. So if I am considering X minus Y equal to 6 into K, where K belongs to Z, K is non-zero, then this ordered pair XY for which X minus Y is multiple of 6 will satisfy both the conditions, because 2 divides 6 as well as 3 divides 6. 2 and 3 both divide 6, and 6 is the least common multiple. So if we consider X minus Y as a non-zero multiple of 6, then condition of R as well as condition of S will be satisfied. So here, because we are having infinite sets, we have to write our condition in this way. We will write that R intersection S consists of those order pairs x, y for which x minus y is an integral non-zero multiple of 6. So we have to answer in that way. Intersection of R and S equal to ordered pair xy such that x and y are elements of given set X and x minus y is an integral non-zero multiple of LCM of 2 and 3, which is 6. So this is R intersection S. For second part B, here our set X is the set of natural numbers, which is infinite set. So in this case, R and S both are infinite sets, and therefore we have to write the representation for R intersection S in this form, because we are not having finite sets for R and S. So this is very easy topic. We can talk about operations on relations, and we can talk about all those operations which we have discussed for sets. So whatever operations we have discussed in set theory for sets, we are going to repeat all those operations on relations here, because relations are nothing but special types of sets. So we will be discussing operations on relations in upcoming lectures in this series. Thanks for watching.